This document describes the video tutorial, which is meant to provide an introductory guideline on the use of the sample size web tool recently developed by the Center for Research on Impact Evaluation, CRIE, on its web page. The web tool is available on the sample size button on the CRIE webpage at the following address. CRIE and DG Employment have developed this tool with the aim of supporting the managing authorities to construct representative samples for collecting data for common ESF and IE indicators. The main purpose of this video tutorial is to offer managing authorities a user-friendly tool for the calculation of the sample size with a view to the ESF regulatory requirements. The users can exploit this tool easily, obtaining the sample size considering different scenarios. The tool primarily focuses on the sample size properties which are required for estimating the correct sample size from the population. In line with the regulatory requirements, the tool calculates the sample size for indicators expressing proportions, for example the share of individuals that have improved their labor market conditions. Typical examples of what is not a proportion are the median income or the mean of the working hours. To have a better understanding of the sample size tool, the user needs to be familiar with few statistical concepts. 1. Population size versus sample. 2. Strata of the population. 3. Confidence interval. 4. Margin of error. With a view to obtaining an optimal sample size design, it is important to describe two types of data sets, A. Population versus B. Sample. The former includes all of the units from a set of information, for instance the administrative data on all pension contributors, while the latter consists of a part of the information that can be drawn from the population. The size of the population is the number of units, for example, individuals, firms, regions, composing the whole population of interest, which will be, usually, larger than the size of the selected sample. So, the fundamental difference between a population and a sample of the population is that the former considers all the individuals while the latter is a representative selection of the first. In fact, due to the sampling method, we observe that a sample has fewer observations than the population. More than one sample can be derived from the same population. As working with the full population is not always possible principally due to both the high cost in running the interviews, and in collecting the data, and the difficulties in dealing with very large database, statisticians often work with a sample of the population, which is composed by only some of the units of this population of reference. In selecting the sample from a population, it is needed that the procedure of individuals selection has to comply with the random sampling method. The simplest random process is characterized by the fact that each individual has the same probability of being selected for the sample. This means that all possible samples of a population are equally likely to occur. This is an important characteristic that allows the researchers to use statistical tools to estimate the characteristics of the population from information observed in the sample. For example, given a simple random sample, researchers can use statistical methods to define the confidence of the estimation, confidence interval, around the mean of the sample. On the contrary, statistical analysis is not appropriate when non-random sampling methods are used. Due to the key role of random sampling in ensuring the representativeness of the sample and thus the reliability of the estimation providing the ESF indicators, the ESF monitoring and evaluation guidance should illustrate the steps of drawing the sample. It is important to emphasize the importance of monitoring the response rate, which is crucial to ensure that the sample is representative. It is worth mentioning that the tool provides the correct sample size in the case of 100% response rate. The response rate is simply the number of people who completed a survey divided by the number of people who make up the total sample group. Suppose a researcher wants to evaluate an intervention on youth employment and, using the sample size web tool, observes that she or he needs to collect data on 2,000 individuals. The researcher then decides to collect the information using the phone, and she or he has a response rate of the 80%, so 1,600 completed interviews. In this scenario, the sample size is not enough to fit the requirements. It is difficult a priori to decide how many more individuals the researcher needs to interview to comply with the sample size provided by the tool. Even though there is no agreement upon standard for a minimum acceptable response rate, the survey methodologists propose different threshold that can be, case by case, changed, by online, 30%, by phone, 80%, by mail, 50%, and in person, 80%. In the previous case, the researcher needs to interview up to 400 more units. In the sampling design method, the sample is constructed starting from the entire, not stratified, population. There are many reasons to divide the population, according to some predetermined characteristics, in a certain number of subpopulations, usually called strata, such that 1. Stratification improves the representativeness of the entire sample with respect to the entire population. 2. It is possible to fix a certain precision of the estimate of the proportion also within the single strata. The characteristics by which the population is divided are often called stratification variables. For example, let us assume that we would like to stratify the population according to both gender and employment status, employed, unemployed, inactive, proportionally to what it has been observed before the participation in a training program. The strata generated on the base of these characteristics are the ones showed in the picture. Statisticians use a confidence interval to express the degree of uncertainty associated with a sample statistic. A confidence interval is a range of estimates combined with a probability statement. For instance, a confidence interval is defined by two numbers, between which a true parameter, that we want to estimate, is said to lie with a certain probability. For example, x1 lower than mu lower than x2 is an interval estimate for the value of the proportion mu. It indicates that the true proportion is greater than x1 but less than x2 with an associated probability. The statistician might use a confidence level to define uncertainty associated with the interval estimate. For example, 95% confidence level means that if we use the same sampling method to select different samples and compute an interval estimate for each sample, we would expect the true population parameter to fall within the interval estimates 95% of the time. Confidence intervals are preferred to point estimates because only confidence intervals indicate a. the area in which the true parameter we want to estimate lies, and b. the uncertainty of the estimate, namely the associated probability that the true parameter occurs in that specific area. In a confidence interval, the range of values above and below the sample statistic is called the margin of error. For example, suppose a researcher wants to study the percentage of adults that train daily, making sure that the 95% of the interval includes the true value of the proportion, confidence level. In addition to that, he wants that each of these intervals has a predetermined length. This length can be fixed by the margin of error that is half of the total length of the interval. This means that if we set the margin of error equal to 0.05 and our estimated proportion is equal to 0.2, our confidence interval will be the range of values between 0.15 and 0.25. The estimates are considered reliable if the margin of error in the population is equal or lower than 0.02 and if the margin of error in the strata is lower or equal than 0.05. These are the minimum requirements that should be set by the users, but the tool allows to set different values of the margin of errors for informative purpose or if the users want to achieve more precise estimates. Finally, the margin of error of the strata should not be considered as the size of the stratum is lower than the 10% of the entire population. However, the tool automatically takes into account the size of the stratum, so no actions are required by the user. Supposes a researcher wants to monitor and evaluate the European Youth Intervention so that she or he needs to define a proper sample size. In the next part of the video tutorial, A series of video tutorial examples will follow. This tool allows computing the sample size needed in the ESF monitoring to achieve a given precision. In the webpage, in addition to the ESF sample size calculator, you can find two different tutorials that help the user to familiarize with the construction of a proper sample. The web tool allows constructing the sample for the common output indicators, the Youth Employment Initiative result indicators and the long-term results indicators. For simplicity, the most part of this video tutorial is about the construction of the sample for the Youth Employment Initiative result indicators. Let's assume that we need to construct the sample for the Youth Employment Initiative in France, in which the participants have been 57,328, and we assume that we want to estimate the proportion of long-term unemployed. Females and males are 24,549 and 29,047, respectively. The starting point is to compute the sample size for the stratified population, allowing a margin of error in the strata of 0.05, a margin of error in the total population of 0.02, and with a confidence level of 95%. Then we click the button Calculate. The web page shows the units that have to be sampled for each stratum of the population in order for the sample to be used instead of the whole population. In this case, the result demonstrates that we need to sample 1,053 females and 1,246 males to be representative of the starting 57,328 participants. In the bottom part of the page we find the total amount of unit and a summary of the parameters set before. A common mistake is to think that the sample size increases linearly with the size of the population. When the size of the population is sufficiently large, the sample size remains almost unchanged when increasing the population. What really matters for the determination of the sample size are the margins of error, in the strata and in the total population, and the confidence level. Let's see the next examples. Before every new computation, remember to use the button New Calculation in the bottom part of the web page. The page will be refreshed. Now we select again the Youth Employment Initiative indicator and we change the population proportionally. Suppose we double the size of male and female individuals, so 49,098 females and 58,094 males, and we leave unchanged the other parameters. The result of the computation shows that the required sample size is increased by just 50 units. Now let's change the proportion between genders, so we double the number of females and we keep unchanged the number of males and all the other parameters. Now we can see that the total amount of units is pretty unchanged, but the proportion of females and males that have to be sampled changes according to the proportion in the new population. In general, the standard confidence level should be settled at 95%. Just for illustrative purpose, the tool allows to change it. In this example we have changed the confidence level to 99% and we have left all the other parameters unchanged. The sample size increases from 3,398 to 4,134. To reach better precision, higher confidence levels and smaller confidence intervals, one needs a larger sample. The tool computes separately the sample size that guarantees the margin of error in the strata and the margin of error in the population, and after it computes the maximum between the two. In our example, what really matters is the margin of error in the entire population. This is simply because the margin of error that we have set in the population is very precise and the precision in the strata is guaranteed as well. See the next example. As said before, if we reduce the margin of error allowed in the strata from 0.05 to 0.03, keeping all the other parameters unchanged, the sample size will remain the same. On the other hand, if we decrease the margin of error in the entire population from 0.02 to 0.01, the sample size will increase from 2,299 to 8,146. Additionally, if we increase both the margin of error in the strata to 0.09 and in the population to 0.05, the necessary sample size will decrease to 382 units. With these parameters, the sample size reacts to reduction of the margin of error in the strata, let's say a reduction from 0.09 to 0.06, as showed here, where the number of observations that have to be sampled increases from 382 to 529. Without additional information, the tool computes the sample size under the assumption that the proportion could take every value between 0 and 1. However, quite often a priori it is possible to reduce the range of the proportion. For example, let's assume that we want to estimate the proportion of young unemployed, and we know that the proportion is reasonably any value between 0.1 and 0.3. If the range of possible values does not include 0.5, the required sample size reduces, as we show in the next example. Here we set all the parameters as in the first example, and after that we click on the bottom Advanced Settings. The web page will show two additional parameters, the first with the minimum value that the proportion could reasonably assume, and the second one with the maximum value. We will insert 0.1 in the first box and 0.3 in the second. As we can see, the required sample size reduces from 2,299 to 1945. The other indicators work exactly in the same way. The only difference is that the population is stratified in more subpopulations. For example, the sample for the CRIE indicator has to be constructed stratifying by gender and category of region with three mutually exclusive categories: more developed region, MR, transition region, TR, and less developed region, LR. In this example, we select Common Output Indicator among the ESF indicators. The table has 6 rows, one for each possible combination of the two stratification variables, gender and region. We fill the population size for each stratum, and we set the margins of error and the confidence level. Finally, we compute the sample size clicking on the button Calculate. The tool will compute the sample size in all the different strata. Note that it is not necessary to fill all the rows in the table. If one or more rows are left blank, the tool will assume that these strata are missing in the population and it will not compute the sample size for them. For example, if the program is implemented in one single category of region, the other categories are left blank. The 4 long-term result indicators refer to different subpopulations, contrary to the other indicators that refer to the whole population. In detail: unemployed and inactive, employed, unemployed or inactive above 54 years of age, unemployed or inactive with any disadvantage. The user could independently decide to construct 4 different samples, one for each of the long-term result indicators using the sheet called Long-Term Result Indicator Simple, or to use the sheet called Long-Term Result Indicators Integrated that jointly takes into account all the characteristics of the population and that guarantees the precision for each of the long-term result indicators. Thank you for watching. If you wish to know more about CRIE methods after watching this, then follow our videos in the YouTube CRIE channel.